My dear student of 12th Science, in my previous physics class, we discussed about Faraday's experiment on electromagnetic inductions. Faraday, during his experiment, observed certain things, and the observations are: whenever north pole of the bar magnet moving towards the coil or moving away from the coil, then the galvanometer gives some deflections. Instead of north pole, if the south pole moving towards the coil or away from the coil, then also galvanometer gives the deflection, but the direction of the deflection becomes reversed with respect to the deflections occur due to north pole. Instead of bar magnet, if the coil moving towards the bar magnet or away from the bar magnet, then also galvanometer gives some deflections. And lastly, if the speed of coil or bar magnet increases, then the deflections of the galvanometer is also increases. So depending on this observation, Faraday gives us certain explanations, and the explanations are: number one, whenever in a circuit or coil there will be a change of magnetic flux takes place in that coil or circuit, an induced EMF is produced. Secondly, this induced EMF exists in the circuit or coil for the time till the magnetic flux linking with the coil or circuit is changes. And thirdly, the magnitude of induced EMF depends on the rate of change of magnetic flux linking with the coil or circuit. So depending on this explanation, Faraday gives us two important laws which are known as Faraday's law of electromagnetic induction. Okay, now see the statement of Faraday's first law. Faraday's first law: whenever there is a change in the magnetic flux linked with a coil, an EMF is set off in it and lasts as long as the magnetic flux linked with is changing. So means according to the Faraday's first law, we can say whenever in a circuit or coil there will be a change of magnetic flux, an induced EMF is produced, and this EMF exists for the time till the magnetic flux linking with the coil or circuit is changing. Now see the second law, Faraday's second law. The magnitude of induced EMF is proportional to the rate of change of magnetic flux linked with the coil. So therefore, according to Faraday's second law, we can measure the magnitude of induced EMF in a coil or circuit. According to the Faraday's second law, the magnitude of induced EMF or coil in a circuit is proportional to the rate of change of magnetic flux linking with the circuit. Okay, now we have to derive the mathematical form of Faraday's second law by which we can measure the magnitude of induced EMF in a closed coil or circuit. To derive that formula, you have to know another important law of electromagnetic induction known as Lenz law. Now see the statement of Lenz law. The direction of induced EMF or current is such that it will oppose the change of flux producing it. So therefore, according to Lenz, we can predict the direction of induced EMF or current in a coil or circuit. According to Lenz, in a coil or circuit, the EMF will induced such a way that it will oppose the rate of change of flux producing it. Now see the mathematical formula of Faraday's law by which we can determine the magnitude of induced EMF in a circuit or coil. Let at any time flux passing through a coil is phi and its number of turns is n. Therefore, we consider a coil having the number of turns n, and through that coil the flux passing is phi. So therefore, total flux linking with the coil is n phi. According to the Faraday's second law, the induced EMF in this coil is given by E proportional ddt of n phi. Ddt of n phi means this is the rate of change of magnetic flux linking with the coil, or E proportional n into d phi by dt. N is the constant term, which is the number of turns in the coil. Now in this expression, if we introduce the Lenz's law, then this expression becomes E proportional minus n d phi by dt. This minus sign indicates that the induced EMF occur in a circuit such a way that it will oppose the rate of change of magnetic flux, or E equal, there will be a proportionality constant K, minus sign remain as usual, then n into d phi by dt. This K is a proportionality constant, and the magnitude of this K depends on the unit system. In the SI unit system, the value of K is 1. So therefore this expression becomes E equal minus n d phi by dt, and this is known as the mathematical form of Faraday's law, by which we can measure the magnitude of induced EMF in a closed circuit or coil. Now from the definition of magnetic flux, we know that d phi equal B vector dot ds vector. Therefore this above expression can be written as E equal minus n. In place of d phi we can write B vector dot ds vector. So therefore E equal minus n B vector dot ds vector by dt. So this is the another mathematical form of Faraday's law of electromagnetic induction in terms of magnetic field, Now student, you have to know the integral form of the Faraday's law of electromagnetic induction. Integral form of Faraday's law of electromagnetic induction. To know about the integral form of Faraday's law of electromagnetic induction, we consider A is a circuit which is situated over the magnetic field B, vector. S be the surface bounded by the circuit. Therefore, phi equal, that is a magnetic flux linking with this surface, is given by integration S B vector dot ds vector. What is ds vector? ds vector is the elementary area of the surface S, which is bounded by the circuit A. So therefore d phi by dt equal integration S dB by dt dot ds. So this is the rate of change of magnetic flux. Therefore the induced EMF in the circuit due to changing magnetic flux is given by, from the Faraday's law we know that E equal minus d phi by dt is equal minus, and d phi by dt is equal this. So therefore minus S dB by dt dot ds vector. So this is known as the integral form of the Faraday's law of electromagnetic induction. Now there is a very important things you have to remember. The induced electric field produced in the loop due to changing magnetic flux is given by integrations over closed E vector dot dl vector equal minus d phi by dt, Also you can say this is another form of the Faraday's law in terms of electric field, So this is the integral form of Faraday's law of electromagnetic induction. Now student, already we read about a law, that is Lenz's law. Remember, the Lenz's law always obey the principle of conservations of energy. So therefore Lenz's law and the conservations of energy. How can you explain that? the Lenz law obey the principle of conservation of energy. See this situation very carefully. Here we consider a solenoid, and with this solenoid a galvanometer is connected. There is a bar magnet, and this is the north pole of bar magnet. You imagine that whenever north pole of the bar magnet moving towards the one face of solenoid, and that face of the solenoid becomes south pole, then what happened? So if this face of the solenoid becomes south pole, between this south pole and north pole there will be a force of attraction exist, and due to this attractive force the bar magnet automatically move towards the solenoid, by which there will be a change of magnetic flux takes place and some induced current or EMF will produce. But this is against the laws of conservation of energy. Why? To produce the induced EMF or current, we have to give some external energy. But in this situation, without any external energy, automatically bar magnet moving towards the solenoid, by which there will be some induced EMF will produce. Means therefore this situation is totally wrong. So therefore, according to Lenz, this face of the solenoid becomes north pole, and whenever this face of the solenoid becomes north pole, between this north pole and north pole there will be a repulsive force. Now to move the bar magnet towards the solenoid against the repulsive force, you have to lost some external energy, which is converted into the equivalent amount of induced EMF or circuit in the coil. So therefore these situations obey the laws of conservation of energy. Therefore we can say the Lenz law always obey the laws of conservation of energy, and according to the Lenz law, in a closed circuit or coil we can predict the direction of induced EMF or current. Thank you student. Read all the portions very carefully. This is very important for your exam purpose. Thank you.